Okay, hello everyone. So in this problem we are studying a square wire loop with sides of length 2 meters and it is perpendicular to a uniform magnetic field. Recall whenever we see the word uniform, this means that it doesn't change with position. Half the area of the loop is in the field and it contains an ideal battery with EMF 20 volts. So we have this battery here and it has a voltage or an EMF of 20 volts. We are given the magnitude. We want actually to find the net EMF. We are given that the magnitude of the field is varying with time according to the given equation over here. So B is changing with time. We want to find the net EMF in the circuit. Pay attention, they are asking us for the net EMF. Okay, and this means that we need to check for the battery's EMF plus or minus the induced EMF according to whether they have the same direction or not. So let's start by studying the induced EMF here. We know that the induced EMF has a formula which is minus d phi by dt, and the phi of course is going to be depending on the magnetic field that we have. So remember that phi is BA cosine theta. We are already told that the loop is perpendicular to the direction of the magnetic field. So its normal will have the same direction as the magnetic field. So cosine theta is just 1 and phi will be just B times A. Of course, the area that we will have here is the area of half the square, because whenever we are studying the flux, we are interested in the area through which the magnetic field lines are passing. So this is going to be the area of half the square. And the magnetic field is given by the expression here. So I think we can get now an expression for the flux. So this is going to be, okay, our expression of the magnetic field is 0.042 minus 0.87 T. And the area is the area of half the square, which is going to be L squared over 2, where L is the length of one side. So this is going to be L squared over 2. This is our expression of phi. And now we can get E induced by just finding the derivative of this expression with respect to time. If we look for the derivative of phi, this is going to be, so right here I'm looking for the magnitude, so I will take away the minus sign. So the derivative with respect to time is going to be the derivative of the expression that we got here. And if we derive here, we're going to get, okay, I will take L squared over 2 outside the derivative. And if we solve the derivative, we will just end up with minus 0.87. Of course, I will take away the minus sign because I'm not interested in the directions yet. So this will be the length of the side here of our square is 2. So this is 2 squared over 2 times 0.87. And this will give us 1.74 volts. Of course, this is the induced EMF, and we are looking for the net EMF. First of all, we need to know whether we need to add these two electromotive force values or subtract them, and this depends on the direction of each. Of course, we have now here this magnetic field which is pointing outside the page, but we notice that it is decreasing. So from the expression of the magnetic field, we notice that it is decreasing. So since we have a decreasing field, then phi is also decreasing, then the induced electromotive force will try to generate a magnetic field to increase phi, so it will be supporting the magnetic field. So B induced is out of the page as well, and if we apply the right hand rule, then the induced electromotive force will be anti-clockwise. And we can see here that if the induced electromotive force is anti-clockwise, then we can represent it by this battery here. And it actually adds up to the electromotive force of the battery. So we can actually here add the two electromotive forces in order to find the net EMF. So this will be our value of the electromotive force was 1.74 and that of the battery is 20. So this is 20 plus 1.74 and this gives us a net electromotive force of value 21.7 volts. We are interested in the direction of the net current. Obviously, this is the same as the direction of the total EMF, which is counterclockwise. So for part B, I has the same direction as E induced, which is, or sorry, as E net, because we want the net current, which is counterclockwise. So basically in this problem, we had this loop and the magnetic field was decreasing and thus we had a decreasing magnetic flux. And if we have a decreasing magnetic flux, then by Lenz's law, the induced EMF will try to increase or oppose this change in the magnetic flux. And so it will try to increase the magnetic field and it will support its direction. It will have the same direction. It will give a magnetic field that has the same direction as the initial magnetic field. The initial magnetic field is pointing out of the page, so the induced current will try to induce a magnetic field that is also out of the page. And if the induced magnetic field is out of the page, then by the right hand rule, the current is going to be anti-clockwise, and the induced EMF will also be anti-clockwise.